All right, and we will go from current slide. And we'll even try to turn on the projector and see if it works. In my last class, in the other room, the projector and computer would not communicate. The projector would come on, the computer was working, but the communications were not there. I even came down and got this cord because it worked yesterday, and it wouldn't work down there either. So I don't know if it's their box on the wall or something happened to my computer or what. Let's see. Look at that. Works like a charm. So it's something to do in that room, I think. Okay. So that's settled. Let's hit a few announcements. Okay. Let me start with this one. Oh, maybe I ought to start with this one because it comes first. Now, are any of you over on the Birmingham campus at all? You don't? All right, okay. Now, you may already be aware of this, but if you're not, note, the Leon Kennedy Center is now closed. The Leon Kennedy Student Center is now closed. Everything from the Leon Kennedy Student Center has moved to the new Academic Success Center.
Does that mean the lunchroom?
The lunchroom, that is specifically what it means. The cafeteria is moved. The bookstore, I think, is moved. The Space Center, I think, is moved. I think even police office has moved. I don't know that for sure, but they said here, please note that the Leon Kennedy Student Center is closed. The cafeteria is now operating from the Academic Success Center. So, new location, a little bit further to walk, but that means you burn off some of the calories you just ate, right? Okay, got it. All right, so that's that one. Now, this is the administrative calendar, which usually has stuff we're not really interested in, so I usually don't even print it, and quite often I forget to print it, or it's too late in the month and I don't print it, but I printed it this time. Nothing coming up immediately that you need to be aware of. I thought this would be on it, but it's not. Does anyone know what tomorrow is? What? L Day. That's Lawson Day. That means there's going to be food, music, games, just the general, hopefully it's a little warmer than the day type outdoor stuff going on, okay? Now, I know on the Birmingham campus, I know several things going on. Don't know for sure everything on this campus, but hopefully you'll see or hear about it. Are any of you involved in student government or any other committees that do L Day? No. Okay. Watch out for it tomorrow. Wear your Lawson paraphernalia if you've got it. You know, it's a fun time. I may even wear a t-shirt and tennis shoes and jeans. You know, it's that fun, you know, so, and any excuse will do. Okay. The rest of the stuff we'll get to later, but this one I think you do need to know about now, okay? Not this coming Thursday, day after tomorrow, Thursday, but next Thursday, the 11th, is the Honors and Awards Day. It's over on the Birmingham West Campus, the Arthur Shores Fine Arts Building, which also is our gymnasium. Strange Fine Arts and Gym. But anyway, it's usually in the morning, which sadly means we probably won't have class that Thursday the 11th. Hey, okay. So anyway, I'll find out more details later. Like I said, usually it's in the morning. I haven't seen anything about it. I'm sure it's somewhere out there. I checked emails yesterday. I didn't get far enough along to find out. Yeah. It's what? 10. And this class starts at 10. Okay, so we will not have class next Thursday. Okay? This Thursday we will. We'll be here. But it's next Thursday we will not. Okay? And that's a school activity, not something I came up with. Now, this is something I think some of you, and I hope some of you, will be interested in. NASA's Community College Aerospace Scholars. Okay? You'll see that little thing on the above the map there, NCAS. That's what this is talking about. NASA Community College Aerospace Scholars Program. It starts in the fall, but the deadline for applying for it is next month, May the 15th. So look into it. You can Google that, you can search for it, you can find all sorts of information, or on this flyer that I printed off, there are at least 2 different websites, with one website, 2 different locations on it, 3 different locations you can go and find out more about it, okay? A few people here at Lawson have participated in it before, and from what I understand, they had a blast with it. That's a blast, no. Okay, but it was, from what I understand, it was a really good program. You actually get to interact with some of the space missions. I mean, it's incredible what you get to fiddle around with. You learn a lot, but it's a lot of fun. So look into it. It's a great program. If you want to see this flyer, to get the information from it, you certainly can. Okay? I'll have all 3 of these flyers up here so you can look at those to your heart's content. Okay. I'll do that later. Forgot to mark my absences in my last class, but I can figure those out. Okay. Any questions before we get going today? I have a dumb question for you. What's the past tense of spring break? Any ideas? Make a guess. For me, spring broke. Okay? We did our taxes over spring break. And I've confirmed something that I had long suspected and really knew in my heart of hearts. We are not wealthy. Okay? And I found that out because the tax rate that we got was a tax rate for the wealthy. We didn't come close to that, okay? Whereas usually my wife and I try to get it so we owe a little bit at tax time. We don't like to pay out more than we have to, so we usually shoot, and every year since we've been married, I think, we've been around $1,000 to $2,000, no more than $2,000 that we owe at tax time. This time, it's between $8,000 and $9,000. It's a big tax rate. And guess what? We even paid estimated taxes because we were afraid this was going to happen. We still owe to write a check between $8,000 and $9,000. So it's tax broke for us this spring break, the aftermath. So I hope you and your family came out better than we did. But just about everyone I've talked with here, same thing. Whatever they got last year, if they got money back, they owe money now. If they owed a little before, they owe more this time. So it's nice tax break we got, isn't it? Okay, never mind. That's political. Okay, we are on example 3, and I'm pretty sure they don't have example 3 on here, so that's why I had it at that place. Any questions before we get started? All right. Be thankful that our projection works. The last class, I recorded it, but it was only audio because I couldn't do the video. I had to do right on the board for the people who were here in class, and so people who were home only got to hear what we were doing, not see what we were doing. Y'all get both, and the people at home get both this time. All right. We're going to derive, not that we'll ever use it, a triple angle formula. It says rewrite sine of 3x in terms of sine x. ITO means in terms of sine x. Okay? How in the world can we do that? Any ideas? Any guesses of a first step? Anybody? What might you try? Second? Okay. Any ideas? First, let's do this. Sine of, what is 3x, at least with it in terms of x? That's a dumb question, but it's a really simple answer. it's 2x plus 3x is 2x plus x. Oh, that's not bad, is it? Okay. Now, this is a sum angle formula. We can do that, can't we? Oh, yeah. Long spring break ago, wasn't it? Okay. What is this sum angle formula? Anyone remember it? Sine of anybody? 2x times cosine of x plus cosine of 2x times the sine of x. Well, we got one sine x in it anyway. Not a lot of progress there. It makes it look really much worse. But we do know a double angle formula both for sine and for cosine. So let's put those down. What is the sine of 2x? What's that double angle formula? Anybody remember? Two times the sine of x times the cosine x, and then that's multiplied by cosine x from above, right? Got it? Now, cosine 2x. Remember, there were three different renditions of this. One was cosine squared minus sine squared. That has cosine in it, not only sine. So let's not use that. The other one had cosines only, but not sines. We want it in terms of sines only. Does anyone remember the cosine 2x formula in terms of sines only? And you can look this one up. I don't remember this one in my head either. What is that one? Is that a little louder? 1 minus 2 sine x. Is that what you said? Sine squared x, right. Okay, sine squared x, right? And that's times sine of x. Hey, folks, looky here. We're much closer. Here we only had one sine x. We wanted it in terms of sine x. Here we only had one. Now we've got 1, 2, 3. Okay, so this is good. But we still got, well, what's cosine times cosine? Cosine squared x. And guess what we can do with that? Let's go on and multiply this through. This will be sine x minus 2 sine cubed x. Okay? I just distributed the sine x into that parenthetical expression. But what is cosine squared x in terms of sines? 1 minus sine squared. Perfect. We're almost there, folks. This is 2 sine x times 1 minus sine squared x plus sine x minus 2 sine cubed x. All right? Now we just got one more distribution to make. This will be a 2 sine x minus 2 sine cubed x plus sine x. Ooh, that's ugly. Okay. Minus 2 sine cubed x. Okay. Get out of there. Combine like terms. That gives us 3 sine x, right? Those two. Minus 4 sine cubed x. Looky there. Hey, that's what the book got to. Good for them. Okay? See how that works? All right. All right. Here's area, right? Gotta find you. There you are. All right. Anyone else come in? Hold on. Okay. We just did example 3 on the bottom of page 382. Okay? Any questions? Can I move on? Okay. So the next topic is power-reducing formulas. As if we hadn't got enough formulas under our belts yet. We need a bigger belt. Okay. Power-reducing formulas. The double angle formulas can be used to obtain the following power-reducing formulas. Okay? Now, I don't know if you remember or pay too much attention to them. Let's see how this works. Let's go back a step. Let's think again for our double angle formulas. And really the only one we're using is the cosine. Cosine of 2x is equal to, anyone remember this one? Especially the one that is got sines and cosines in it. What was that one? Anyone remember? Minus sine squared x. Okay. Now what does that look an awful lot like? If you had a plus sign rather than minus sign, what would that be? Your Pythagorean identity. How does that go? 1 is equal to cosine squared x plus sine squared x. Right? Everybody in agreement? All right. Now, what happens if you if you add those two equations together? What do you get? The left-hand side becomes 1 plus cosine 2x. The right-hand side gives you 2 cosine squared x, because these add to 0, right? Well, what you can do now is divide both sides by 2. And that would give you cosine squared x, that squared, is equal to, I think I like it in just that form, 1 plus cosine 2x, that's not squared, cosine 2x divided by 2. And let's see. Ha! Cosine squared x is equal to 1 plus cosine 2. Oh, I'm sorry. Cosine squared u is equal to 1 plus cosine 2u over 2. Yeah. There we got it. Piece of cake, right? Okay. Now, let's go back to that one. And this time, rather than adding the two equations together, let's subtract the two equations. So let's do minus the bottom equation. Okay? Which, if you carry the minus sign through, that would be a minus here, a minus there, and a plus there, right? Now we'll add them, because we just negated them. So what does the left-hand side become? 1 minus cosine 2. You want to go back to u's rather than x's? Okay, we'll do u's, because the next slide uses u's. I don't know why. And then these two cancel out, and you get 2 sine squared x, u, okay? Now divide both sides by 2, and you get sine squared u is equal to 1 minus cosine 2u over 2. So you go from a second power to a first power. Different trig function, but it's still first power. And sure enough, that's what we got there. Sine squared u is equal to 1 minus cosine 2u over 2. Now, the tangent. Do you remember the tangent double angle formula? You don't need to. Because what is tangent squared x? U, isn't that sine squared u over cosine squared u? Yay or nay? Okay. Well, sine squared u was 1 minus cosine 2u over 2. And cosine squared u was 1 plus cosine 2u over 2. You can multiply numerator and denominator by 2 and wipe out the 2's, and you have that tangent squared u is 1 minus cosine 2u over 1 plus cosine 2u. And let's see if that's what they got. Look at that. That's what they got too. All right? So you see, these are really easy to get. Okay? And there we have power-reducing formulas. Yay! What good are they? You know. Okay. I was kidding. No, I'm just kidding. Okay. They allow you to reduce powers. But what they also do is come up with a half-angle formula. Because you can now say that the sine of 1/2 u is 1 minus cosine u, or make it v. Let u equal 1/2 v. Is that okay? So this would be sine squared of 1/2 v is equal to 1 minus cosine of v over 2. So there we have a half-angle formula. And if you don't like it squared, just take the square root out. Okay, and you got it. And that's what good they are, is to come up with a half-angle formula. Because we had a double-angle formula, why not have a half-angle formula as well? Okay? So that will give us our half-angle formulas. That's about the only good I see of them. They'll make up something that you could do it with too, but that is another thing you could do. All right. So here's an example, example 4. We're going to use that. Rewrite sine 4th x, and you wouldn't be able to do this without a power-reducing formula, in terms of first powers of cosines of multiple angles. So how do we do that? From what we just said, sine 4th x, isn't that the same as sine squared x squared? Yay or nay? Yeah, same thing, right? What was our sine squared x? We had that. What was it? Anyone remember? 1 minus cosine 2x over 2 squared, right? All right. Well, let's square those things and see what we get. Numerator squared would be what? Anybody? I'll do the first one, 1, okay? Next. Twice the product of the 2. Minus 2 cosine 2x, right? Then square the last one. Plus cosine squared of 2x. Got it? Over square the denominator, you get a 4. Okay? Now it says rewrite sine 4th x in terms of first powers of cosine of multiple angles. Here we got a first power of cosine of multiple angles, but here we have a second power. We want first powers. So how do we deal with that cosine squared 2x? Anyone remember what that is? That's 1 plus cosine double it 4x over 2. Right? That's your power-reducing formula for cosine squared. So let's see if we can put all that together, and what do we get? 1 minus 2 cosine 2x. That's perfectly fine. That's just what we want. Plus 1 plus cosine 4x over 2, and all that is over 4. Okay? That's a little awkward looking, isn't it? So I think, what's that? Yeah. So let's multiply the numerator here by 2 and multiply the denominator by 2. That's legal in most states, right? Because 2 over 2 is 1. Okay? So what will we get then? We'll have 2 times 1 is 2. Okay? Minus 2 times 2 is 4. Cosine 2x. Get out of there. Okay? And then this 2 will divide out that 2, and you have a plus 1 plus cosine 4x. And all that is over 8. Okay? And we can combine like terms here, and that gives us 3 minus 4 cosine 2x plus cosine 4x all over 8. Rewrite sine 4th x, that's what we started with, in terms of first powers of cosines of multiple angles. In terms of first powers of multiple angles. There we have it. Now, we could, let's see what the book does. They pull out the 1/8 in front, which is fine. So sine 4th x is equal to 1/8 of 3 minus 4 cosine 2x plus cosine 4x. Okay. Sorry. Ran into it. Okay. And that's how they left it. You don't have to write it that way, but I did just to show you it's the same. They show via a graphing calculator display how this looks, and sure enough, what they did, they graphed this first and this second, and the graphs went on top of each other, showing they're exactly the same. You can't see it because they're on top of each other, but I'm glad they showed us that. And there is a checkpoint after every example. There was on the last one, there is on this one. Any questions? Now, some cynic in the front row said, what good is this? Okay, the little symbol they have there is sort of suggesting you're going to use it when you get to integration. This is pre-calculus algebra. When you get to calculus, those of us that will get the calculus, you will be using some of these. So there is a future for it somewhere out there. All right. Now, let me erase all this so you can see how they did their work. See if they found an easier way or did it more same way or a little more. Okay, so they started the same way we did. Sine 4th x was sine squared x squared. We know that, property of exponents. And then we expanded the sine squared x to be 1 minus cosine 2x over 2, but then still had to square that. And when we squared it, they pulled the 1/4 out, which is fine, and left with a 1 minus 2 cosine 2x plus cosine squared 2x. Well, that would be fine, except they wanted it in terms of first powers only. So we need to work with that cosine squared 2x, and they came up with that being 1/4 times 1 minus 2 cosine 2x. That was fine, but the cosine squared 2x became 1 plus cosine 4x over 2. And then they basically doubled this, put that over 2, doubled that, put that over 2, then pulled out the 2 and made it 1/8, and that gave them, oh boy. Yeah, I would have done it this way. 1/4, so they pulled it out, then they multiply back through. Fine. Minus 1/2 cosine 2x plus 1/8 plus 1/8 cosine 4x. Good for them. All right, then they combined like terms and got 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x, then pulled out the 1/8 and made it 3 minus 4, because 1/2 is 4/8 minus 4 cosine 2x plus cosine 4x. Yes, I see this much clearer now. Right. Okay. It works. Any way you do it. As long as all your steps are right, it works. Okay. Any questions on that? I wouldn't have done it this way. I didn't do it this way, but that works too. Any questions? All right. And let's go to, here's the, you can use a graphing utility to check that result. Shown below, notice the graphs coincide. You can't see it, but you just have to take the word that the graphs graph right on top of each other. And there they are. And you know that sine 4th x is never negative, so sure enough, it has to always be positive or 0. Okay. Now we get to the half-angle formulas, which is what one excuse I had for doing power-reducing formulas. I said it was about the most reasonable one. So if we go from what we just said, and just like we said, we had sine squared x was 1 minus cosine 2x over 2. Well, if you change the x to let u over 2 be x, then 2x would be 2u over 2, which would be u, okay? So this, and this is squared, so take the square root of both sides. So you wind up with a plus or minus here. How do you deal with the plus or minus? Depends on which quadrant this is in. If this is in the first quadrant, you use the plus. If this is in the second quadrant, you use the plus. If this is in the third quadrant, use the minus. If this is in the fourth quadrant, use the minus. So the plus or minus is you use depending on where the function is. This one, with the plus up here, if it's in the first quadrant, use the plus. Second quadrant, use the minus. Third quadrant, use the minus. And fourth quadrant, use the plus. And for the tangent, SpaghettiOs, okay? They changed it around, haven't they? Let's go back to the tangent for a moment. Here's how they wrote tangent squared before, okay? What they're going to do now is take a square root of this and change this to u over 2 and make these u's, okay? But then you have a fraction inside a radical, okay? So that's usually not a very positive thing to have. So how did they jump from this to that? Well, let's sort of make that flying leap here, okay? So this becomes tangent squared of u over 2. I'm changing from u to u over 2. That's equal to 1 minus cosine u over 1 plus cosine u. Okay? And I'm going to take a square root of both sides. So that gives us the plus or minus here. All right. Well, a lot of times they don't like having radicals in denominators or denominators in radicals. So how you clear this, anyone have a clue? A guess? Multiply it by what? By the conjugate of the denominator. Okay, there's your denominator. Multiply it by its conjugate. Anyone remember what that is? 1 minus cosine u. Multiply this by that same thing, 1 minus cosine u. Okay. Now this looks like it's just getting messier, doesn't it? Well, let's see. So this will be plus or minus the square root of, well, this is just 1 minus cosine u squared. Hey, we can just take that out of the radical, can't we? Okay. What does the denominator become? A conjugate multiplied by itself, what does that give you? Okay. You can FOIL it if you want to. That would be 1. And when you do the innards and the outwards, the outwards minus cosine u, the innards plus cosine u, that adds to 0, and then the last is just going to be minus cosine squared u. What's 1 minus cosine squared u? Anybody? Sine squared u. So what we have here is plus or minus, but it really doesn't matter. 1 minus cosine u over sine u. Because the square root of a perfect square, this is sine squared u. The square root of that is sine u.
Square root.
Okay. All right. This is what we have. Right?
Why did you put in square root?
Okay, because we're doing the tangent rather than the tangent squared. Okay. You take the square root of both sides. All right? Because this is tangent squared, I want a tangent of u over 2. I also changed the u's to u over 2, so that became a u over 2 here, but u's here. Right. Now, so that gives us the formula there. Well, that looks perfectly fine, but they gave us two formulas. Okay, you got that firmly implanted in your mind now, right? 1 minus cosine u over sine u, okay? One minus cosine u over sine u. Well, where did that come from now? Okay. Well, we'll go back and do the same thing again. Well, not quite, but close. Oops, too far. Okay, this one. All right. Because I'm going, okay, we can do it here. What we're going to do here is multiply by the conjugate again. But this time we're going to do it in the numerator, which you say, why? Well, just to see what happens. 1 plus cosine u, but in the denominator you got a 1 plus cosine u. Okay? Well, this again gives us 1 minus cosine squared u over sine u times 1 plus cosine u. Right?
They equal the same thing. Why are we writing it twice?
What's that?
They simplify to be the same thing. Why are we writing it twice?
Okay, I couldn't understand. My hearing's bad.
Do we have to write both answers?
No, I'm just showing you can write it either way. Okay? What is 1 minus cosine squared u? Anybody? Sine squared u. So this is sine squared u over sine u times 1 plus cosine u. But this sine u will go into one of those, and that gives you sine u over 1 plus cosine u, which is the second form they have here, sine u over 1 plus cosine u. So you can use either one of these two forms. They're exactly equivalent. They are the same thing. You don't have to worry about the signs here because they take care of themselves. You know, sine u or cosine u, depending on what quadrant it is in, it will always work out the same. Up there, you have to decide which sign you're going to use, depending on the quadrant where u over 2 lies, where it lives. Okay. So those are your half-angle formulas. Do I memorize these? Nah. If I need them, I'll look them up, or I may remember how I got them. Okay? It's a little convoluted, but it's not too bad. But you can always look them up. So we have sum formulas. We have difference formulas. We have double angle formulas. Now we have half angle formulas. Do we have enough formulas? Okay? Never. Okay? Let's see if we can use this in an example. Find the exact value of sine 105 degrees. They want an exact value, not an approximate. Not look it up on your calculator and see what you get. They want an exact answer. How in the world can we do that? 105 is not one of our favorite angles, is it? Those are your 30, 60, 30, 45, 60, and 90. Okay? And then in the other quadrants. 105 is way over somewhere else, but it's not one of those. But what is twice 105? 210. 210 is 30 degrees beyond 180, isn't it? Ha! So this, we'll use our half angle formula. This is the same. This is the sine of 210 degrees over 2, right? And then your half angle formula is what? It'll come back, hopefully. Yes, there it is. Okay. What's that half angle formula? Starts off with a plus minus, doesn't it? Square root of, how did it go? Just back one. Just look just above you on the page. What's that formula? 1 minus cosine 210 in this case, right? And we know that, or we'll figure it out in a minute, over 2, right? Now, first thing we have to do is decide whether we use the plus or the minus. Well, what we're looking for is sine of 105. Where does 105 live?
Oh, second quadrant?
Second quadrant. And what's the sign in the second quadrant? Positive. So we're not going to mess with the minus. It's just going to be positive. So this is going to be the square root of 1 minus, and what is the cosine of 210? Okay. Again, second. I like to draw pictures, as you may have realized by now. 210 is just beyond 180, right? It's, goodness gracious, this thing's a pain in the neck. There we go. Okay, it's just beyond 180. How much beyond 180? Here's 180. 210 is how much beyond 180? 30. So there's your reference angle. So we want the cosine of 30 degrees, but in this quadrant. What is the sine of cosine in the third quadrant? The sign, S-I-G-N sign. Either plus or minus.
Oh.
Negative. It's negative in the third one. Remember, cosine, all students take chemistry or calculus. Cosine is positive here. Positive of those two, negative of those. So the cosine is going to be negative here. So it's going to be a minus, which is going to be plus. And what is cosine of, you were answering that question. What's cosine of 30? Root 3 over 2. So that'd be 1 plus root 3 over 2 over 2. There's the exact answer, but that's sort of ugly, isn't it? Okay, so let's multiply numerator and denominator by 2, and that would give us the square root of 2 plus root 3 over 4. That's still a little ugly, so let's do the square root of 2 plus root 3 over 2. I don't know if I can make it any prettier than that, okay? And that's not very pretty. But let's see how they did it in the book. I can't find it. There it is. The square root of 2 plus root 3 over 2. Yes. Not pretty, but, and that's an exact answer. In order to get to what that number is approximately, you do a square root of, on your calculator, usually open a parenthesis for you, 2 plus the square root of 3, then close that parenthesis, and then divide by 2. You'll get an approximate answer. I don't think they even gave you that in the book, did they? No. Okay. But that would be how you get the exact value for that. As soon as you put it in the calculator, that's an approximate value, but that would be exact. And the cosine of 30 is root 3 over 2 in the third quadrant. You put a minus sign there, so you'll minus plus there. All right, any questions? And by the way, there is another checkpoint right after that one. All right, let's see how they did it. They seem to come up with ingenious ways of doing it that can make it really a simple concept seem really complicated, but okay. Let's erase this ink. Everybody got it? Okay. See how they did it? Begin by noting that 105 is exactly half of 210. 210 is one of our favorite angles, or a multiple of that, or whatever, related to that, one of our favorite angles. So we'll use that, the half angle formula. Sine of 105 is the square root, the positive square root, because 105 is in quadrant 2 and sine is positive there. So it's the positive square root of 1 plus cosine 210, which we do know exactly, divided by 2. And that would be 1, and cosine of 210 is negative, so it would be 1 minus a minus, which is 1 plus, square root of 3 over 2. And if you multiply the numerator and the denominator by 2 under the radical, you'll get 2 plus root 3 over 2 squared, which would be 4, but since that's under a square root, just pull out the square root in the denominator and leave it like that. The positive square root is chosen because sine of 105 is positive in quadrant 2. Good deal. Any questions? Everybody got it? All right. Now, if you thought some of the others were perhaps wondering why you did them, this makes me wonder even more, okay? But you really do use these some. But if I ever need them, I'll look them up. But let's just go over them. The product to sum and sum to product formulas. They're going to start with product to sum formulas. This is the top of page 385. Okay? All right. Each of the following product to sum formulas can be verified using the sum and difference formulas. Okay? There's a little part of me that says, show them how you got these. But the bigger part of me says, just look them up. Okay? And yes? Oh, we did, didn't we? Thank you. I saw that and then blew it. Forgot about it. Okay. Let's do example 6 here. All right. Find all the solutions. Yeah, I'm glad you pointed this out. Solving a trigonometric equation. Find all the solutions of this equation. 1 plus cosine squared x. Oh, man. I've got to sneeze something fierce. Is equal to 2 times cosine squared x over 2. On the interval 0 to 2 pi. All the solutions on that interval from 0 to 2 pi. Okay. Now, one problem you might see here is here you have cosine of x, or cosine squared x. Here you have cosine squared of x over 2. We need to get the arguments to be the same thing. So, I think it's easier to go from half angle to angle than it is to go the other way. Do you agree? Especially since it's already almost set up for us. If we go back and remember, actually the power reduction formula, or the cross of that and your half angle formulas. In fact, I would say let's just stick with the half angle formulas. Cosine of u over 2, but you got the square of it, so that's going to blow your square root away. So cosine of x over 2 is equal plus or minus the square root of 1 minus, right? No, 1 plus. Okay, I always forget that. 1 plus cosine x, okay, over 2.
So if you're doing cosine squared, you just lose the square root. So cosine squared x over 2 is equal to 1 plus cosine x over 2. But then, if you multiply it by 2, 2 times this is just going to wipe that out. So your right-hand side here is just simply 1 plus cosine x. Do you see that? No. Okay. Did you see this? Okay. Back up one slide. Cosine of u over 2 is plus or minus the square root of that, right? Okay. Now, on the next thing, it's going to be cosine squared of u over 2, or x over 2, right? Okay. Right here, this is cosine squared of x over 2, right? Well, cosine squared of x over 2 would just be squaring this, which is losing the square root. That would be 1 plus cosine x over 2, right? Okay. That's what I did up here. 1 plus cosine x over 2. But this has a 2 in front of it. So let's put a 2 in front of that, and you lose the over 2. Okay. So now you got this thing here is just 1 plus cosine x. So this thing is 1 plus cosine x. So now we have 1 plus cosine squared x is equal to 1 plus cosine x, right? Left-hand side we didn't mess with. The right-hand side we messed with and got that, right? Now, I'm going to subtract 1 from both sides. There we go. All right. Now I'm going to also subtract cosine x from both sides. Okay, and this gives me cosine squared x minus cosine x is equal to 0. What would you suggest I do next? Say again? You may have said it right, I can't hear. Say again? I can't hear.
I don't know what it's called. Yeah.
What you say? Ooh, we could do that, but let's not. What have we got here? We have a quadratic equation, all in cosines x. If you use a Pythagorean identity, that's going to become a sine squared x. And then you got sines and cosines, and it's even worse. So this is all in terms of cosine. Factor, okay? Factor out what? Cosine x. And what do you have left? Cosine x minus 1. And that's equal to 0. And what do we do with that? Anybody? Second? Set each one of them equal to 0. Because if you're going to have this thing multiplied by that thing to give you 0, either that's got to be 0 or that's got to be 0. No other way you can multiply two entities together and get 0 as an answer unless one of them is 0. So we set each of them equals to 0. So this says either cosine x is equal to 0 or cosine x minus 1 is equal to 0. Well, what values between 0 and 2 pi will cosine be 0? Where is cosine equal to 0? Cosine starts at 1. It becomes 0 at...
Sine 0. So sine equals 1. Cosine equals 0.
Okay, yeah, where sine's equal 1, cosine's equal to 0. And where is that? But what? Pi halves, exactly. There's 1, pi halves. Any others?
3 pi over 2.
3 pi over 2, perfect. 3 halves pi. And that's the only two places it is between 0 and 2 pi. All right, over here, what can we do with that? Add 1 to both sides. And that gives us cosine x is equal to 1. And where is that true between 0 and 2 pi?
at 0, so x equals 0. And that's the only place it's equal to 1 until you get back at 2 pi, but 2 pi, that's the parentheses there, so we don't include 2 pi. So here are 3 answers, either x equals 0, x equal pi halves, or x equal 3 halves pi. Okay. And that's what the book got to. Good for them. Thanks for pointing that out. Okay. And they actually show a graph of that as well. And those are the 3 places where it intersects the x-axis. Good deal. All right, any questions? All right. Let's go now. Thanks for finding that, because that was a good problem to solve. And let's go to product to sum formulas. Okay. Now notice here it says these can be found, verified using the sum and difference formulas. I'll show you how that comes about. Let's first do the product. We want sine u, sine v. Okay? Well, where does that show up? Which one of our sum angle formulas or difference angle formulas does sine u, cosine v show up? The sine has both sine and cosine in it. The cosine has only cosines and only sines. So that's where it shows up. Cosine of u plus v. Anyone remember what that one is? Cosine u, cosine v, minus sine u, sine v. And if you put the minus in there, cosine u minus v, that is cosine u cosine v plus sine u sine v. And if we're looking for the sine u sine v, then what we do is subtract the top equation from the bottom equation. I should have put the bottom one on top, and then it would have made more sense. So this will become a minus, that'll become a minus, that becomes a plus. Okay? All right, then add them together, and you get cosine of u minus v minus cosine of u plus v, and these go to 0, is equal to 2 times sine u sine v. So the product is then half of that. And that's exactly what they get here. The product here is 1/2 of cosine u minus v minus cosine u plus v, which we just got. Okay. Added the two of them together, you get the cosine. Okay, go back to that we just did, and rather than subtracting the top one, add the two together. You lose the sine, use sine v, and you get 2 of these is equal to the sum of those two. So divide by 2, and that gives you cosine u cosine v is 1/2 the cosine of u minus v plus the cosine of u plus v. And then to do the sine u cosine v, use the sine, the sum formula and the difference formula, and the sum gives you, is from adding those two together and taking half of it, and the cosine u sine v is taking the difference of those two. You just go back to those basic formulas and manipulate them till you can isolate the product. So this gives you products to sums. Of course, the sums or differences, okay, are pretty convoluted, okay, but they're all there, okay? And again, do you ever really need these? Yeah, when you get into integration, you will. But you'll look them up. I'm not going to suggest you memorize them unless you're just a great memorizer. You love to memorize. If you got that room in your memory banks, more power to you. Mine have been full for many years. Nothing else will fit in there. In fact, I'm losing most of what was in there before. So I'll look them up. Okay. So here's example 7. Rewrite the product of cosine 5x sine 4x as a sum or a difference. Well, this is cosines and sines, so this is going to be a sum of sines, okay? Well, actually, a difference of sines, okay, because the cosine comes first. This is the fourth one over here. This one, that one right there. Cosine u sine v, okay? And how that is this cosine 5x sine 4x is equal to 1/2. Remember that's in there. And it's sine of 5x plus 4x, I believe, 9x. Let me go back and check. Yep. You add them together. Minus is the difference here, the sine of x, because then you subtract the two. You see, sine of the sum minus sine of the difference. And the sum of 4x and 5x is 9x. The difference is that. So that's all you can do. It's 1/2 the sine of 9x minus the sine of x. Sorry, that's all you can do to it. But that's all we're going to use them for, is to get a product into a difference, and you can integrate the difference much easier than you can integrate a product, especially when the product has different arguments. Okay? But you don't know how to integrate yet, so don't worry. Take my word for it. That's easier than that. Okay? So let's see. I think that's all they do with it. So let me erase this, and we'll see what they did. The cosine 5x sine 4x is 1/2 of the sine of 5x plus 4x minus the sine of 5x minus 4x, which is 1/2 the sine of 9x minus 1. They distributed the 1/2 the sine of x. Believe me, those are easier to integrate than that every time. Okay, so that's where you will use these formulas when you're integrating products of sines when they're different, sines and cosines with different arguments. But when do you ever do that? Yeah, I mean, you may. And if you ever do, this is how you do it. Okay. Now, there is a checkpoint. Please do the checkpoint. Now we have sum to product formulas. And for the life of me, I can't think of any place that you really use these, because if you're integrating, these are way easier to do than those, okay, by far, okay. So why would you ever do this, except there are just two more formulas you can do, and what you do with this is use your you basically undo those, okay, kind of. That's basically what you wind up doing, is manipulating those around until you find these, okay. That's not quite true either, okay, because you have to use half-angle formulas here. It's just a mess. If you ever need them, look them up and use them, okay. But I, for the life of me, can't figure out when you would ever need those. But there they are. Okay. Now the unusual thing here is this is a plus, a plus, a plus, that's a minus. And if you followed it through, you'd see that has to be the case. So that just to me is something a little out of kilter. Okay. But again, if you're integrating this, you're going to integrate that, not that. But let's see. For a proof of the sum of the product formula, see the proofs in mathematics on page 396. I know y'all are going to jump to it, right? So let's do example 8. before we get to the application. Okay? We'll come back to the slide, I promise you. Find the exact value of the cosine of 195 degrees plus the cosine of 105 degrees. Okay. And when they say exact value, you got to use one of our favorite little angles. Okay? Now, what might be that favorite angle? Okay? And remember, we had sums and differences. So let's pick something in between those two. There's exactly 90 degrees difference between them, which half of that will be 45. And 45 from 195 would be 150. Hey, 150 is one of our favorite angles, isn't it? That's just 30 short of 180. So that may work. How about 105? Let's see, 105 plus 45 would be 150. Hey, yes, that might do it for us. So let's see. Again, these things, it's so bizarre to ever want to do these. Let's see if we can figure out what that is then. That would be, let's go back to our formulas here. Nope, wrong way. This formula, okay? Okay. Didn't quite do that right. Close, but I mean, it's not bad what we did. But what we want is the sum of these two. We just did the difference. The 190 minus 105 is 90 degrees. That's a good one. What's the sum of those two? 190 plus 105, that would be 195 plus 105, that would be 100, 200, 300. So 190, this is a 95 there, okay. 195 plus 105 is equal to 300, which is again one of our favorite angles because that's 60 degrees short of 360. So reference angle of 60. Okay. Okay. So what's the sum angle of cosines? Do I memorize this? No way. That's this one right here. Okay. So it's twice the cosine of the average plus times the cosine of half the difference. Yeah, I remember those well. Two of my favorites. So this is twice, didn't I say, the cosine of the average, which would be 150, right? 195 plus 105, that's 300 divided by 2. And was it plus or minus? Okay, 2 times the cosine of the average times the cosine of half the difference. Okay, so that would be, I just did it. Oh, oops. It's multiplied. Okay. Yeah. Okay. It's not a minus sign there, it's a times sign. That's what I messed up. Times the cosine of the difference is 90, and half of that is 45. Right? Okay. So twice. And what is the cosine of 150? Well, where does 150 live?
30 below 90. Oh, it lives in second.
Second quadrant, and cosine is positive or negative in the second quadrant. Negative in the second quadrant, and the cosine of 30, since that is your reference angle, is, no, it's minus. I mean, the reference angle is that, but is, reference angle is 30, so that would be root 2 over 2, right? Times cosine of 45. No, I'm sorry, that's root 3 over 2. And this is root 2 over 2. Okay, so one of the 2's goes out, and you have minus root 6 over 2. Okay? Let me get rid of that, and let's see what answer they get in the book. Okay, negative root 6 over 2. Good for them.
So the goal is always to you want it in radians. Typically,
do what?
Whenever we rewrite a product or rewrite an angle, we always typically
okay.
in radians.
What? Yeah, when you have a sum like this or a difference, you add the two together and you subtract the two, and both of those you're going to divide by 2. So see if that comes up to an angle that you like, and hopefully it will. If it doesn't, just do it on the calculator and come up with a partial solution. All right, good deal. Make sense? Because that's what the formulas are. The formulas are sums over 2, difference over 2. Then you have to remember which sine, cosine, which one you do with whatever you know. You go back to this and do what it tells you to.
Yeah.
Okay. So, all right. We ran out of time. We finished example 8, but we didn't get to do example 9. Okay. So we'll pick up there next time. Homework exercises here. We got that close to finishing. Now, I'm sorry that a couple of people left, but I think they already had it. Is anyone here who was not here the Thursday before spring break that you didn't get your Chapter 5 test? Okay. Okay, you need your Chapter 5 test. Don't leave without it. Let me give you your homework exercises first. Any of the odds 7 through 13, they're all at Calc Chat. 9's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat. 21 to 25, 21 or 23, they're both at Calc Chat. 21's at Calc View. Do 25. Any of the odds 27, 33, they're all at Calc Chat. 27's at Calc View. Do any of the odds 35 to 39, they're all at Calc Chat. 37's at Calc View. Do either 41 or 43, they're both at Calc Chat. 41's at Calc View. Either 45 or 47, they're both at Calc Chat. 45's at Calc View. Either 49 or 51, both at Calc Chat. 49's at Calc View. 53 or 55, they're both at Calc Chat. 53's at Calc View. Either 57 or 59, they're both at Calc Chat. And we will stop there and pick up the rest of those next time. Okay, and if you didn't get your third test before the spring break, let me give it to you now. Okay. All right, test 3. Make sure you only got one. Anyone else? Did you get it? Okay. All right. Well, Patrick, we missed him. All right. See you on Thursday. This Thursday.